Hello everyone, this is the final exam review for Math 130, and there's a bunch of questions here, and each of them have a lot of parts for the review at least. So let's just get right to it and see what we can do. I don't have too much space, but I think we can do all these parts for number one. Let's see. So we're asked to solve these equations. They're all linear equations. We have x, t, and b. I'll distribute and simplify for the first one. We'll get 9x minus 6 minus 9. These two will combine. And then that side stays the same. Those combine to 15. And then there's a few things we can do here. Again, the space is kind of limited, but I'm going to add this 15 to that side and simultaneously subtract this 7x to this side. And the whole point here is to move every x term to one side and all non-x terms to the opposite side. So end up with something like this. And we just kind of shift this over here. We end up with 9x minus 7x is 2x. And then here we end up with 12. Divided by 2, we get x is equal to 6. And you can, of course, check this just to verify it's correct. In fact, it's pretty easy to check. 3 times 6 is 18 minus 2. That's 16. 16 times 3 is, I guess that's 48. 48 minus 9, that's 39. And then 7 times 6 is 42 minus 3 is 39. So that checks out. Right? I may not check all the other ones, but let's see. This one, there's no simplification needed. It's already kind of already like that. So again, move all x's to one side. We'll move it to the right, or to the left generally. And then simultaneously move all non-x's to the opposite side. Perfect. That should be a minus 7, sorry. So we end up with 5x is equal to negative 5, divide by 5, and there we go, x is negative 1. Okay, 2 more. Now these next few are some that you have to kind of change a little bit. There's a way around not changing it, but what we can do is we can multiply it through by the denominator to clear denominators, then it will look like the above two looked. Now, something you can do instead is just kind of embrace the fractions instead of get rid of them, and that's, of course, if you're comfortable and familiar with fraction arithmetic, but I'm just going to skip that actually and multiply through by the denominator, which is 3. And if you have multiple denominators, you want to multiply by the LCD, but here there's just a single one. Distributing that will cross-cancel here and just leave us with 2t. And here it's a legit distribution, we get 18. 3 times 2 is 6, so that's 6t. We can actually subtract this 2t to the right side, and we end up with 18 is equal to 4t divided by 4. And that 18 over 4 reduces, I'm going to write it like this, t is equal to, that reduces to 9 over 2. If you want to write that as a mixed number, that's 4.5. 2 goes into 9 4 times. Or if you use your calculator, 4.5, but that's fine. And then, now this one's a little bit of a pain. Very similar to what I did above. I multiplied by the denominator to get rid of denominator. So what you can do here is when you have decimals, you can multiply by 1 followed by as many zeros as you have decimals. So in this case, there's only 1 decimal place for each of these terms, or at most 1. So I'm going to multiply everything by 100. Basically what we're doing is we're grabbing each term and moving the decimal place over once for each term. So for this term, move it over once, to this term, move it over once, to this term, move it over once. And at this point before the distribution, this acts as one term. So moving this over once affects that whole thing. Kind of like how here, I moved the decimal place here, but the b was left alone. This b minus 3 is kind of like the b in that case. So the movement of that decimal takes the hit for both of them. Okay? And you can kind of see that because if you distribute, then you'll get like decimals for 2 terms, but doing that for this kind of distributes that. Anyways, let's see what we get now. We have 158 minus 6b plus 92 is equal to 23 times b minus 3. So I'll distribute the 23. So we get 23b minus 69 on the right side. Here, these two combine. What do they combine to? Well, 2 plus 58, that's 60. And 160 plus 90, that's going to be 250. It's a negative 6b plus 250. So again, now this looks very much like something like we saw here with a and b. Move all b's to one side. I'll move them to the left. Subtract the 23b. And move all non-b's to the opposite side. I'll subtract this 250 to that side. Just like that. Okay, let's see what we get after cancellation. These two cancel, so we end up with whatever those add up to, which is negative 29. Oof. I can't actually see right away what this is. I may need to use a calculator, but let's see. That's going to be 69, 50, well, 6 and 5 added to 11, so it's going to be 31.9, I believe. Negative 319. That sounds right. And then dividing by negative 29. This I can kind of see what's going on. How many times is 29 going to 319, if any? I think it's an even value because if you look at, like, for example, 29 times 10, that's 290. And if you add another 29 to that, you indeed get 319. So this right here is 29 times 10. And this right here, of course, is 29 times 1. So altogether, the result is 29 times 10 plus 1, which is 11. So in other words, 29 goes into this 11 times. The double negative cancels in the fraction, so the answer is b is equal to 11. And of course, that cancels right there. All right, perfect. So that was number 1, and now let's move on to number 2. Okay, so number 2 here is also a solving problem, but they're very specific types of equations. We have absolute value equations here. And something I kind of want to say is that if you have the absolute value of any number equals another number, then that means that the inside is either plus or minus a number. So let me kind of give you an example here. So let's say you have the absolute value of some expression equals a. Well, this implies that the inside expression x is either plus or minus a. For example, if the absolute value of x is equal to 4, then this means x itself must have been 4 or negative 4. Those are both valid solutions, right? The absolute value of 4 is 4, and absolute value of negative 4 is also 4. So, in general, when you have expressions like 1 minus x and 4x minus 2, you do the exact same thing. You say the inside is equal to whatever the outside and the opposite side was, but either plus or minus that. Sometimes you have to check, like in this case we have an x on the outside, so we'll have to check our solution in the end. And I kind of recommend you do that anyways, no matter what kind of equation you have. But let's see how this plays out. And now, by the way, you could also split this into 2 scenarios. The inside is 30 or negative 30, but I'm going to actually use a plus or minus symbol, and I think it's kind of nice seeing it that way. So here we have the inside, 1 minus x, is either plus or minus 30. So I'm going to do it like that. Okay, now to solve for x, I can just subtract this 1 to the other side. So negative x is equal to negative 1 plus or minus 30. And then dividing both sides by the negative 1 in front of this x, like that, leaves us with the following. X is either, so we have to kind of compute each of these. So for the positive case, it's negative 1 plus 30, that's 29 over negative 1. Or, with the negative case, so that's a positive case, let me kind of indicate that above. For the negative case, negative 1 minus 31 is negative 31, and that's over negative 1. So continuing this calculation, we have negative 29 or positive 31. Of course, when dividing by negative 1, the signs change. Now you can check these. But 1 minus negative 29 is 1 plus 29, which is 30. The absolute value of that's 30. And 1 minus 31 is negative 30. The absolute value of that is also 30. So they both check out. Now here something kind of funny happens because you have an x on the outside as well as on the inside, but the process is exactly the same. So you set the inside equal to plus or minus the outside value. Which again makes sense because if the inside is positive that, then this absolute value is that. But if the inside is negative that, the absolute value cancels that negative in front, and you still get that. Some people mistakenly look at something like this and think the absolute value of 4x minus 2 is equal to 4x plus 1 by changing the signs. Of course, absolute value of a negative is a positive, and that does hold, but when you have 2 terms like this, the absolute value doesn't actually work necessarily. For example, if you plug in 0, you can clearly see that, or maybe not, 0 is not a good idea, because 0 you get negative, so 0 works actually. But if you plug in something like 1, you get 4 minus 2 on the inside, which is 2, absolute value of 2 is 2. But when you plug in 2 here, you get 6, and those are clearly not the same. Well, I meant to say when you plug in 1. So plug in 1 here, you get 6, plug in 1 here, you get 2. So yeah, that doesn't work actually. So instead what you do is you just set the inside equal to plus or minus whatever the thing is on the outside, like I said earlier. Now, here it's a little hard to see what's going on because you have like 2 cases and it kind of gets funny. So for this one, unlike with the above where I was able to use a plus or minus symbol, here it's going to be really weird and hard to follow. So for this one, I actually am going to split it into 2 cases. Either it is the plus case or the minus case. We'll solve for x in each of those cases, and then we'll check our answer for each of those x values. So we're going to get two solutions. So the plus doesn't need to be distributed, so I'll just get rid of it like that with the parentheses. Move all x's to one side and all non-x's to the other, just like we're used to from the previous problem. These cancel, that's 5x. I added 2, sorry, I don't know why. There we go. Divide by 5, we get 7 over 5. Okay, that's one solution. Now the other guy here, if you distribute this negative, we get 4x minus 2 is equal to negative x plus x. Move all x's to one side, all non-x's to the other, just like that. So we get 3x is equal to negative 3, divided by 3, and x is equal to negative 1. So now let's check these by plugging them in. They actually both work, I think. So notice when we plug 7 over 5 into this, we get 4 times 7 over 5, which is 28 over 5. Minus 2, you can think of 2 as 10 over 5, right? It's 2 over 1, we'll multiply by 5 to get this, or you can see that that reduces to 2. So this is 18 over 5 in the end. The absolute value of that's that still. And then what's 5 minus 7 over 5? Well, 5 is 5 over 1, which you can write as multiply top bottom by 5, you get 25 over 5. Minus 7 over 5, and yes, indeed, 25 minus 7 is 18, so you get 18 over 5. Now, negative 1, 5 minus negative 1, that's a double negative, so that's 5 plus 1, so that's 6 on this side. Plug a negative 1 here, you get negative 4 minus 2, that's negative 6 as well. The absolute value of that is positive 6, so it actually does check out. So they both work, so I'm going to write my answer as a comma-separated list. X equals 7 over 5, comma, negative 1. Fantastic. So now let's move on to number 3. Okay, so number 3 here is a little different than the previous ones. Of course, we're finding the equation of a line satisfying the following things. So there's 3 different parts here, of course. Now, the first part is going to be a little more difficult than these. That's probably not the best choice of words. It's going to set the tone, really. So the way we're going to establish A is the same way we're going to establish B and C. B and C are, I think, a little trickier because of the wording parallel and perpendicular. So maybe these are actually more confusing, but the reason why I said more difficult is because there's kind of more work here, but here it's kind of trickier. Really, they're kind of the same amount. I'll stop talking, let's just get to it. So what I want to do is I want to use point slope. Point slope, if you don't remember, is y minus y1 equals m times x minus x1, where m is the slope, x1 and y1 is part of a point. We have 2 points here, and we want to use 1 point with a slope, but we don't have a slope. Of course, you could find the slope if you had 2 points, and we do. So how we do that is we'll use a slope formula. M is equal to the change in y values over the change in x values. I think of rise over run, like y's over x's. Rise is vertical, which are y values. Horizontal would be x's. So that's run, so those are x values. Okay, so I'm going to label these as xy, xy, just like that. The first one will label 1s, the second one will label 2s. So we have x1, y1, and x2, y2. There's a lot of ways of doing this, and this one's kind of nice, as we'll see. The first step here is to find the slope. And the way I'll do that in this case, because we have 2 points, is I'll use slope formula. So m is equal to y2 minus y1, negative 3 minus 2, over x2 minus x1. So that's negative 1 minus 0. It's negative 5 over negative 1, which is positive 5. So we end up getting that m is equal to 5. Perfect. Now we have the slope. We move on to the next step. The next step is to use point slope with one of the 2 points. I'm going to use the first point, and in fact, if you think about it, the first point has an x value of 0, so it's on the y-axis, meaning it's actually a y-intercept. Since we have slope and y-intercept, we can actually just use slope-intercept form. So the answer should be y is equal to 5x plus 2, but I'm going to use this just so we can see it in use. So we end up with y minus the y value. So this is x1, y1 in using that. And by the way, you could use this point as well. You can use either one of these points, and at this point you relabel it as x1, y1. So the red labeling is for this formula, which I already used in step 1, so that labeling is kind of gone now in step 2. So y minus y1 equals the slope, which is 5, times x minus x1, which is 0. That's just 5x. And of course, if you add this 2 to the other side, you get y is equal to 5x plus 2, which I mentioned is kind of visible already at the very beginning because coincidentally this is a y-intercept. Okay, so that's nice. Now B and C are kind of similar. Of course, they involve different wordings, but the process is exactly the same. The way you do the first step is a little different, but the way you do the second step is exactly the same. So the first step is to find the slope. I'm not given the slope, but I am given the point. So how do we find the slope? Well, we're parallel to this equation. But what does parallel mean? Parallel means the slopes are the same. So slopes are equal. So let me write that above. So slopes are equal. That's what parallel means to me as far as slopes go. If two lines have the same slope, they never intersect, so they're parallel. So if I can find the slope of the equation we're parallel to, according to this, they're equal. So it will be the same as the slope of the line we're trying to find, the equation we're trying to find. So I'm going to grab this and move it over here and convert it to slope-intercept form. So how do I convert this to slope-intercept form? Well, slope-intercept form is y is equal to, I'll write SIF for slope-intercept form. Y is equal to mx plus b. Basically, this says when y is by itself, the number in front of x is the slope. So how do I get y by itself? I can subtract that 2x to the other side, just like this. And then finally, we can divide everything by negative 3. So we go y is equal to negative 2 over negative 3 is positive 2 over 3. 5 over negative 3 is negative 5 over 3. So there's a weird fraction y-intercept there, but that doesn't matter. What matters is this number. This is our slope. Since this is the slope of the line we're parallel to, it must be also the slope of the line that we're trying to find the equation of. So altogether from step 1, we get m is equal to 2/3. Perfect. So now in step 2, I'm going to use point slope with the point we're given, which is 6, 4. So label that as x1, y1. Use it with point slope with the slope we just found. Y minus the y value equals 2/3, the slope, times x minus the x value. Distribute that 2/3. We get y minus 4 is equal to 2/3 x. Okay. What's 2/3 times negative 6? Well, it's negative. And over here, I'm going to just notice that 2 over 3 times 6, by cross cancellation, 3 goes into 6 twice. So we're left with 2 times 2, which is 4. So this is 4. Ah, look at that. Adding 4 to both sides cancels the 4s. So we're just left with y is equal to 2/3 x. Fantastic. Great. So the process, again, is pretty specific. So something to keep in mind. Now with C, it's the same thing. Only the wording means something different. So parallel means slopes are the same. Perpendicular means the slopes are negative reciprocals. Negative reciprocals. Sometimes people call them opposite reciprocals. Of course, negative and opposite mean the same thing. They have opposite signs. So we'll find the slope of this guy, take its negative reciprocal, and that will be the slope of the line that we're trying to find the equation of. So again, to find the slope, I'm going to grab our equation that we're perpendicular to. 5x minus y is equal to 3. Convert this to slope-intercept form by solving for y. That's pretty simple. Just subtract the 5x. You get negative y by itself. Multiply everything by negative 1. We get y is equal to positive 5x minus 3. The number in front of x is 5. That's the slope of this equation, not our equation, because of the word perpendicular. Only in the parallel scenario they're exactly the same, but in the perpendicular scenario, they're negative reciprocals. So we take the negative reciprocal of 5. 5 is, as a fraction, 5 over 1. So the reciprocal of 5 over 1 is 1 over 5. So the negative reciprocal of 5 is negative 1 over 5. So not only do you reciprocate the fraction, well, the number as a fraction anyways, but you also change its sign. If it was negative, then we would change the sign to positive. Okay? And if it was like 2 over 3, then it would be 3 over 2, reciprocal of that fraction. So we have the slope. Now we'll use our point with point slope and the slope we just found. So it's x1, y1. So we have y minus the y value equals the slope, negative 1 over 5, times x minus the x value. Distribute negative 1 over 5 times x is negative 1 over 5x. Okay. Negative 1 over 5 times negative 5 is positive 1. The 5's cancel completely and you just get 1. Double negative is positive. Add this 3 to the other side. We get negative 1 over 5x plus 4. And that is the final answer. Just like that. Awesome. Great. So that concludes number 3. Now let's move on to number 4. All right. So for this question, we're asked to find the x and y intercepts. So this relates to the graph of these equations, but this is still a very algebraic question. So x-intercepts is when y is 0, and y-intercepts are when x is 0. So just set each of them equal to 0 one at a time, but don't forget to write the actual point that the solution corresponds to. So let me show you what I mean. For x-intercept, we're going to set y equal to 0. And in doing so, right away, we get 5x is equal to 40, of course, because 4y is 0 and y is 0. Divided by 5, we get x is equal to 8. Now, that corresponds to the point 8, 0, because, of course, x is the x value of the point, and y is the y value of the point. So we have 8, 0. There we go. So now for y-intercept, you do the exact opposite. You set x equal to 0. So when x is equal to 0 in this equation, the x term goes away. We get negative 4y is equal to 40. Right? Don't forget the negative. Divide by negative 4. These cancel. We get y is equal to negative 10. So the point that this corresponds to is x equals 0 and y equals negative 10. And now moving on to b. Now for b, the y-intercept is actually easier to find first in this case. With a, they were kind of the same. This is of course, in standard form. The reason why y-intercept is easier here is because in slope-intercept form, you're given the intercept. But of course, if you just let x equal 0, you see that it kind of comes out exactly the same. 3 over 5 times 0 is 0. 0 minus 9 is negative 9. So this corresponds to the point 0, negative 9. Okay? For x-intercept, it's a little more complicated, but we know what to do. We're going to set y equal to 0. So we'll get 0 is equal to 3 over 5x minus 9. So there's a few ways of doing this. You can multiply by 5 if you want and then solve that. But I'm actually going to keep the fraction until the end. So I'm going to add this 9 to that side. So we end up getting 3 over 5x is equal to 9, and kind of flipping things. Okay. Then we're going to multiply both sides by the reciprocal of the number in front of x, which is 5 over 3. Why are we doing that? Well, the 5's and 3's cross cancel, so that ends up working. Really what we're doing is dividing by the number in front of x, just kind of like we usually solve. But notice dividing by a fraction is the same as multiplying by its reciprocal, so that does the trick. Also, if we were to clear denominators by multiplying by 5, then we'd have 3x and we'd have to divide by 3 in the end. So really it ends up being the same thing. Okay. Now on this side, 3 goes into 9 3 times, and 3 times 5 is 15. So that means x is 15. So the ordered pair solution, which is the point, is 15, 0. Of course, the x value we got, comma the y value we got. Okay. Sometimes for these kinds of questions, people misinterpret this and write like them as an ordered pair, 8, negative 10. That's something completely different. In fact, there's no real name for that. That's just kind of like jumbling up things in a weird way. So don't do that, please. Now here, this is very similar to A actually. So for the x-intercept, we'll have y equals 0. So we end up with 2x is equal to 3. Divide by 2. X is equal to 3 over 2. So the ordered pair solution here is 3 over 2, 0. Right? X is that, y is 0. Good. For the y-intercept, very similarly, we let x equals 0. So when x is 0, we get negative y is equal to 3 right away. So multiplying by negative 1, or dividing by negative 1, however you want to see it, it's the same kind of thing. We get a cross, we get a double negative on this side. So multiplying this by negative 1, I guess you can write it like that. You get double negative, so it's positive y, but here you get negative 3, so that corresponds to 0, negative 3. Awesome. Great, so that finishes 4. Now let's move on to problem number 5. Okay, so in this problem here, we're asked to solve the system of equations and also state our method. Now, I usually like to label each equation in the system with a 1 and 2, so that way this is 1 and this is 2, just so I can refer to things. And this I'll also call the 1 and 2 here. Now, notice that as far as forms of lines go, for the second one, they're both in standard form. But for this one is standard and one is slope-intercept form. Basically, since y is by itself in one of these, in 5a, I probably want to use substitution. So I'm going to use the substitution method. And why substitution works is because since y is by itself, we can plug it in for y in the other equation. I'm going to plug this into this guy. So the result will look like this. I'm going to write equation 1. Only I'm going to write out 1, but when I get to the y part, I'm going to write what y is equal to from the other equation in parentheses. So we have 4x minus 6y equals 16. And notice I left a gap for the y, and now we're going to replace y with what it's equal to from the other equation, which is, of course, x minus 4. We can distribute this negative 6. Don't forget to distribute the negative sign as well if you have one. We have 4x minus 6 plus 24 is equal to 16. These two combine to negative 2. We can subtract this 24 at the same time, might as well. So we get negative 2x is equal to, those cancel. That's going to be negative 8. Divided by negative 2, we get x is equal to positive 4. Perfect. So if x is 4, what is y? Well, we need both in order to have an actual solution to the system. So we can plug that back into either of them, but since y was already by itself in equation 2, that's very suitable. So I'm going to plug that back in here. So when x is equal to 4, we get y is equal to 4 minus 4, which of course is 0. So if x is 4 and y is 0, we have the ordered pair solution 4, 0. And you can check this satisfies both equations in the system. Notice 0 is equal to 4 minus 4, we just saw that. And here, 4 times 4 is 16 minus 6 times 0, that's a 16 minus 0, which is 16. Fantastic. Now here, since they're both in standard form, I probably want to eliminate. So I'm going to use elimination here. Now you can also use substitution if you want. You don't have to use elimination. In fact, what's nice is that since there's no number in front of x for either of these, you can solve for x in either one and then plug it into the other one. So for example, if you add 9y to the other side, you get x is equal to 9y plus 73, and then plug the 9y plus 73 into x from equation 1, for example. But here we can either cancel the x's out or multiply the top by 3 to cancel the y's out. So I'm actually going to cancel the x's out, but to do that, the signs are the same here. So I need to subtract to make the signs opposite. So I'm actually going to show that process. So the top will leave the same, and the bottom we're negating each term. So change the signs of each term. Negative, positive, now negative. So I hope we see what I've done. Everything that was positive is now negative, and everything that was negative is now positive. Great. So adding straight down, the x's cancel out. And for the y's, those combine to 12y. And what do those combine to? Is that 48? No, it's not quite. It's 30. I guess it's 38, which is not that great, but okay. So it's negative 38. Okay, divide by 12. That reduces. It reduces by dividing by 2. So we get y is equal to 19 over 6. That sounds kind of strange. Should we go with it or should we think a little more? I think it. Wondering if this would have been an 83, so that's 48. So 12 goes into 48 evenly, and you get a nice number opposed to this weird fraction. But I'm going to go with this weird fraction instead of changing the problem. And now what do? Well, we could eliminate y's and then get x. That actually works. Or once we've used elimination once, we can plug back in and use substitution. So if I wanted to plug that back in to find x here, we can definitely do that. We're going to get nasty fractions regardless. So you know what? I'm going to eliminate again. So to eliminate again, I want to eliminate y now. So first I eliminated x, but now I want to eliminate y. So to do that, I'm going to erase this. I hope that's okay. We did that here by negating the bottom. So to cancel these y's, the signs are already opposite, but the numbers are not the same. So we have the opposite problem with x. But if we multiply the top by 3, then we'll have positive 9y, negative 9y. The y's will cancel and we iterate down. So let's distribute that 3. We get 3x plus 9y is equal to 35 times 3. Let's see, that's going to be 105. And then the bottom one stays the same, but notice the 9y's will definitely cancel out. So we get 4x is equal to whatever those add up to, which is 178. Divide by 4. Does that reduce all the way? Not really, because 78 divided by 2 is 139. Sorry, 78 divided by 2 is 39, is what I meant to say. 100 divided by 2 is 50. 50 plus 39 is 50 plus 39, that's 89. So this actually reduces to 89 over 2. So that's not the funnest answer, but okay, it definitely works, I think. I say I think because I'm not going to check it, but you can check it. I don't know if you're actually going to do that or not. But plug in this x value and y value into each of these and you'll see that it works. In fact, it's kind of nice for the bottom one here. Well, I guess for both of them, you get cancellation. Notice that 9 over 6 reduces to 3 over 2. So you multiply that and you'll get negative 38 over 2. And then 89 minus 38. Oh, you know, it's a plus because of the double negative, isn't it? So it's 89 plus 38. Hopefully you get double this, which is 146. And it sounds like that's right. But again, you can check that on your own. I'm pretty sure there are no mistakes here, but that part's kind of iffy. I'm pretty sure there may have been a typo there, actually, now that I think about it more. But it's okay. I'm going to leave it like that. I've demonstrated the method of elimination there. So great. So now I'll move on to number 6. Okay, this question here is actually fairly straightforward. We're just asked to multiply these polynomials out. And essentially, it's a distribution or double distribution or FOIL or whatever you want to call it. Here, it's legitimately FOIL because it's first, outer, inner, last, and all that. So the way I normally explain it is you double distribute. So you distribute the 3x, then you distribute the negative 4, and then you combine like terms. Here, this is not a FOIL technically because there's more terms than just the first, outer, inner, and last. So the way to see it is exactly how I described here. Distribute x first to each of these 3, then distribute this negative 2, and then combine like terms as needed. So let's take a look at that. So x times x squared, that's going to be x to the 3rd power. X times 3x, negative 3x, is going to be negative 3x squared. X times 4 is going to be 4x. Okay, we're done distributing x. Now let's distribute this negative 2. Notice negative 2 times x squared is going to be negative 2x squared, so I can actually write that below here to combine like terms. Negative 2 times negative 3 x is positive 6x, and then negative 2 times positive 4 is negative 8 finally. Adding straight down, we get x cubed, negative 5x squared, positive 10x, and then minus 9. Perfect. What does it mean to square something? It means to multiply by itself. So you can write this as 2x minus 1 multiplied by itself, and then FOIL that out, just like I described here, which is, again, just a double distribution, but it's the first 2 multiplied, outer 2 multiplied, inner 2 multiplied, and last 2 multiplied, or FOIL for short. So 2x times 2x is 4x squared. 2x times negative 1 is negative 2x. Negative 1 times 2x is negative 2x. Negative 1 times negative 1 is positive 1. These two combine to negative 4x, so we end up with this. Now there is a shortcut to remember a binomial squared, and that is the first one squared, 2 times the product, and then the last one squared. So notice 2x all squared is 4x squared. Their product is negative 2x, so 2 times the product is going to be negative 4x in the middle, and then negative 1 squared is positive 1, so it's plus 1 at the end. Okay, FOIL this, we get 2x times 3x is 6x squared. 3x times 1 is 3x. Negative 4 times 2x is negative 8x. Okay. Negative 4 times positive 1 is negative 4. These combine to negative 5, so there we have it. Awesome. Now this last one's kind of funny because it is, again, a FOIL problem. But what's funny about it is if you think the opposite of factoring, when you factor a trinomial with x squared in front, you look for 2 numbers that multiply to the last one and add to the middle one. But on the other hand, going backwards, if you have 2 binomials that have x in front with no number in front, like here there's a number in front of x for each of those, but here there's not, you can just write out x squared plus the sum of these two numbers times x, which is 16x, plus the product of those two numbers, which is 16. And it's that quick. If you want to actually FOIL it out, do so. You'll get x squared, 6x, 10x, those combine to 16x, and then 6 times 10 is 60 finally for the last term. Great, so that was 6. Now let's move on to number 7. Okay, so here we're asked to factor, completely factor. So that means you don't just factor a little bit, factor as much as you can. So what I'm going to notice for this first one is that these numbers in front, these coefficients, 7, 49, 56, can all be divided by 7. So we can factor a 7 out. But furthermore, the lowest power of n is 7, so we can pull out 7n to the 7. So let's see what that looks like. So what I want to do is I want to divide each of these numbers by 7 and simultaneously subtract each of these powers by 7. So 7 less than these. So 7 divided by 7 is 1. N to the 9 minus 7 is 2. And you can just check as you go along with distribution. Distributing this back in gives you indeed the first term. So the second one, 7 times negative 7 will be that 49. N to the 7 times n to the 1 will be n to the 8th. So there we go. And then 7 times negative 8 is negative 56. And then you don't need any more n's. The n to the 7th distributive will give you back this n to the 7th. So there we go. So we factored a little bit anyways. But to factor completely, we need to check if this trinomial left over can be factored. And this one actually can. How we know is because since there's no number in front of the square term, all we need to do is look for numbers, two numbers, then multiply to the last term, negative 8, and add to the middle coefficient, which is negative 7. And of course, the two numbers that do the trick are 8 and 1. Specifically, negative 8 and positive 1 work. Right? These two numbers multiply to negative 8 and simultaneously add to negative 7. So that means we can actually factor that, leaving that 7 into the 7 on the outside. This factors as n minus 8 times n plus 8. N plus 1, sorry. And you can check, you can totally check this. FOIL out this, distribute the 7 into the 7 back, and get exactly the original trinomial. Fantastic. B. B is a little harder because there's a number in front of the x squared term. There are a lot of shortcuts here, but what I'm going to do is use the AC method. Now, the reason why it's called the AC method is because the number in front of the squared term is A, the number in front of x is B, and then the other term is C. They're like quadratic formula, ABC. So the AC method says to multiply A and C. We're going to do that in this case. 6 times 15 is 90. So it's going to be negative 90, in fact, because of the negative 15. So we look for two numbers and multiply to that and simultaneously add to the middle coefficient, which is technically negative 1. Okay. Now, I'm actually going to write that over here just for space, if that's okay. But I hope you see where I got these things. Okay. But now, okay, so there's a few ways to continue from here. But what we want to do now is we want to do the same thing we did above. We want to look for two numbers, then multiply to this and add to this. Now, of course, 9 and 90 is 9 times 10, and they have a difference of 1, so 9 and 10 actually do the trick. 9 and 10 work. To make the signs work, it has to be negative 9 and positive 10. Now, there's two ways to go from here. One way is longer than the other, but some people actually like it more. And that is to look at those numbers, attach x to them, and split the middle term up using those. So don't write the middle one, and instead replace the middle one with 9x minus 10x. Let's scoot that over a little bit more. There we go. Now, first I've noticed that makes sense. 9x minus 10x combines to negative x, negative 1x. But now what's magical about this is that now we get this, these kind of two pairs of binomials that actually factor in a nice way. That you can factor by grouping, basically. So what you do is you can pull out what these both have in common, which is the 3x. What we have left over is 2x squared plus 3. Here, these both have a 5 in common, but they're both negative, in fact, as well. So divided by negative 5, you get 2x plus 3. And there shouldn't be a square here, by the way. pulling a 3x out, 6 divided by 3 is 2, and removing an x from the x squared leaves us with 2x. So also the kind of hint I saw there is that they should be the same. And in fact, notice they do match. So we can now factor this out. What we have left over is just 3x minus 5. So imagine this as basically a binomial. They both have the 2x plus 3 factor in common. So if you factor that out, you get 2x plus 3 times those guys, 3x minus 5. And that is the answer. Not too bad. What's the other way I was talking about? Well, there's actually kind of a shortcut. And what you do is you do exactly what we've done, only you draw a line through this x. On top, you write the front number without the square, and then reduce these as fractions. This one reduces by dividing by 2 to 3x over negative 5. This one reduces by dividing by 3 to 2x over 3. Now, these fractions fully reduced correspond to those binomials. 2x over 3 is 2x plus 3. 3x over negative 5 is 3x minus 5. Quicker, but something more to remember, I think. So people generally like this because there's actually math in between and it makes sense. So it's nice to practice that. Okay, now C is a funny story because you can actually, believe it or not, you can do this in the exact same way we did this. The only issue is that you have to write it in descending order first. And you have to include the missing term, which is 0a. Factor out the negative, because when we apply these techniques, we want the front number to be positive always. And then this works out perfectly. You can use the AC method. You get 100, a negative 100. The two numbers are multiplied to negative 100, but add to 0, or negative 10 and 10. You can apply a grouping or super x, or I call it super x. You can use this weird shortcut method, and that works. But that's not the way to go. Even though it's great and it works in general, that's not the way to go for this problem. Maybe some of you already know this just by looking at it, but this is a difference of squares. So how you can tell is when you have a binomial that's separated by a minus, and the two numbers are squares. You can square root them. So it's pretty easy to recognize that, and they pop up fairly often in algebra. So I can tell right away the square root of 25, kind of give it away. Square root of 25 is 5. Square root of 4a squared is 2a. So what you do is you square root these numbers with a minus in between and then with a plus in between, and that always does the trick. This is just a classic example of difference of squares. A minus b times a plus b always falls out to a squared minus b squared. Great. So with that being said, that concludes 7. Now let's move on to number 8. So for number 8 here, we're asked to solve, these are quadratic equations. Now quadratic equations are a lot more complicated to solve than linear equations, as we'll soon see. And basically what we want to do is move everything to one side so the zero's on the other, and, well, factor the non-zero side, set each of those factors equal to 0, and then solve each of those. So that's basically what we'll be doing. Now you can also use quadratic formula, completing the square. These are all valid ways of doing this. But since we just got off of 7, which was factoring, we're kind of in factor mode, so to speak, I'm going to do each of these with the factor method. And in fact, I think there are other problems in the review that may involve the other methods, but we'll see those when we see them, obviously. So I'm going to move everything to one side so the zero's on the other. So I'm going to subtract this 25x to the left and add this 24 to the left. So change those signs to bring them to this side. So the 0 is now on that side. Now we're going to factor this, look for two numbers and multiply to the last one and add to the middle one. And of course the numbers at work are 24 and 1. It's negative 24 and positive 1, in fact. Multiply to, so actually they're both negative, my mistake. So to multiply to positive, they either have to be both negative or both positive. But in this case, since they're both the same sign and add to a negative, they must both be negative. So that means this factors is x minus 1 times x minus 24. Perfect. And then from here, we're going to set each of these factors equal to 0. So we're going to set x minus 1 equal to 0 and that equal to 0. Why is that? Well, it's a thing called the zero product property, or sometimes referred to as zero factor theorem or zero factor property, just kind of depending on the book. or who you ask, I guess. But if you have two things to multiply to 0, this only happens if one of those things was 0 itself. So if x minus 1 is 0, you can write that out and actually add 1 to the other side. You get x is equal to positive 1. Similarly, if x minus 24 is 0, add 24 to the opposite side and you get x is equal to positive 24. Now, a very quick way of solving x minus something equals 0 is just changing the sign to a positive. Similarly, if you had x plus 2 as a factor, x equals negative 2 would be the solution. And furthermore, if there's a number in front of x, then you divide by that as well, because if you had something like 2x minus 3 is equal to 0, we know how to solve that. We add that 3, which is the change in the sign I was talking about, and then dividing by the number in front of x. So in essence, all we do is change the sign of this guy and then divide by any number in front of x. So that's kind of the shortcut. And we'll see that here with this one. So move everything to one side so the zeros on the other. Okay, this requires AC. 4 times 21, that's 84, so it's negative 84. So what two numbers multiply to negative 84 and add to 25? Negative 25. Well, actually a few ways to factor 84, but we're looking at one of them that works. 4 times 21. In fact, we kind of have to be careful because although 4 times 21 works in some sense because 4 and 21 add to 25, you can't make any sense of the signs. Because if they multiply to negative, one of them was negative. So since the result's a negative, the larger one must be negative and this one positive, but then these combine to negative 17. So it's a little trickier than just looking at what we have. So what I'd like to do instead is I'll actually factor 84 in the following way. I'll write 1 times 84, 2 times something, 3 times something. I'll just go on as far as I need to go. And then I'll either add or subtract these numbers depending on the sign of what we're multiplying to. So I'll explain that in a moment. So let's see. 84 divided by 2 is 42. 84 divided by 3. Well, we'll get to that. We'll get to that in a moment. 84 divided by 4, that's 21. 84 divided by 5 doesn't work. 6 we can do. So this is interesting, but if you divide this, if you multiply this by 3, 2 by 3, you get 6. And if you divide 42 by 3, 42 divided by 3 is 14. And then 7 times 12 is 84. And now maybe we can talk about this 3. So if you divide this 6 by 2, you get 3. And if you multiply that 14 by 2, you get 28. So you kind of have to balance them by dividing one by a number and multiplying the other by that same number. You get that other way of factoring 84. Now I believe this is it. You can try 8, 9, 10, 11, 12, and so on. The next one that will work, I think, will be 12. But notice 12 is a repeat of this. Right? You get 12 times 7, that's a repeat of 7 times 12. So this is a unique set of factoring 84 into two numbers. Okay? So now what we're going to do is we're going to subtract these numbers. Why subtraction? So we'll put a minus on top. The reason why is because these two numbers, whatever they are, they'll multiply to a negative, so they have opposite signs. Now when you add two numbers with opposite signs, you're really subtracting those numbers. So we're looking for a 25 as a result. Now I'm just going to do bigger minus smaller. 84 minus 1 is too large. 42 minus 2 is too large. 28 minus 3, there's our guy. So we're going to use 3 and 28. Perfect. So 3 and 28 work. To set the signs up right, that's positive and negative. We'll do the trick. I'm going to use my shortcut I explained in the previous problem. So we're going to write the 4t without the square on top. Reduce them if you can. The first one cannot be reduced. What's kind of funny about that is that if you don't even bother reducing the other one, just knowing one of the factors will automatically give you the other one. Let me try to show that here. So we get 4t plus 3 from the fraction that did not reduce. And then notice, to try to complete this, 4t times t will give you 4t squared, and 3 times negative 7 will give you negative 21. From here, you change the signs to negative 3 divided by the 4, so we get negative 3 over 4, kind of like I explained here. change the sign of the number, divide by the number in front of the variable. Here, change the sign of -7 to +7, and these are our solutions. Okay, so I kind of skipped a little step here. So I said t minus 7 works. Now, if you wanted to check by reducing, notice 4 over 28 reduces to 1 over 7, so that'll be t over -7, which exactly corresponds to that. So great. This one's kind of funny because we can do things the same way we did A, but you could also just think about it kind of. It's hard to show work for that, but think of how -2 can be factored. Okay, either this is -2 and this is 1, or this is -1 and this is 2. Yeah, so I'm trying to think how to make sense of that. Well, maybe this could be 1 and -2, like switching it out like that. Yeah, I don't know if that quite works actually, but it's a thought. Now, if b is 1, then this will be 1 minus 3, and that's -2, so that works. But if b is 2, not -2, -2 would work because you get -2 minus 3, and that's not 1, that's -5. But if b is 2, then 2 minus 3 is -1. So those multiply to this. So the values that work for b are either 1 or 2. So it's kind of strange, but that works. You can kind of see this by factoring the number if the other side is factored already. Now, that doesn't actually work if you have numbers in front of b and fractions and so on. That's kind of hard to manipulate and factor those fractions, but it's just an idea. So what I'm going to do instead is I'm going to distribute this and simultaneously add that -2 to this side. So we get b squared minus 3b, now plus 2 equals 0. The two numbers are multiplied to that +2, which is our last term here, and simultaneously add to -3, or of course -2, -1. There's no number in front of the b squared, so we didn't need to use AC, and we don't need to use a super x way. We can just do this right away. Okay, so we end up with b minus 1 times b minus 2 equals 0. So using that zero product property we've been using, right away this tells us that b is equal to the opposite signs of these numbers, which are 1 and +2. Just like I agreed, or we agreed on earlier. And with that being said, I'll move on to number 9 now. Okay, so now for number 9 here, we have these 3 radical problems. So to solve these, what we want to do is first isolate the radical if it's not isolated already. With these it is, but with this one it's not. We have to subtract 5 first. And then once we've isolated the radical, all we really have to do is take both sides to the power of the index of the radical. So if it's a square root, then you take both sides to the second power. That undoes the radical. If it's a cube root, you take both sides to the third power. That'll undo the radical. So here, it's already isolated. We'll square both sides. What we end up getting is that the radical cancels with the square on the radical side of things. So we end up with x minus 2 is equal to 5 squared is 25. Add this 2 to the other side, so we get our answer is then x is equal to 27. And you can check this pretty easily with the original equation. 27 minus 2 is 25. The square root of that is indeed 5. Now you do have to check, because if this was -5, for example, -5 squared is still 25, so you still get the same solution. But plugging it back in, you'll get 5 is equal to -5, which isn't true. So you have to be a little careful. So here, the radical is isolated. It's a cube root, so we'll cube both sides. Okay. The cube and the cube root will cancel out. Perfect. So we're left with this thing on the inside, 2n squared minus n minus 2 is equal to 2 cubed, which is 2 times 2 times 2. 4 times 2 is 8. Subtract that to this side, so we get 10. Kind of skipping ahead. There we go. So we get 2n squared minus n minus 10. Now, I explained in the last few problems how to factor this by the AC method and so on. I'm actually going to use guess and check here. I'm going to throw us for a loop, but just to kind of demonstrate other factoring properties. So I'm going to notice that 2n squared will come from 2n times n. Now we have to check a few things, because what two numbers multiply to 10, you have a few options. It's either 2 and 5, 5 and 2, or 10 and 1. And the general rule of thumb is to use numbers that aren't too far apart. So 1 and 10 are probably out for the count. I'm going to use 2 and 5. I'm just going to pick an order and then check the inner and outer products. I don't know the signs, so I'll hold off on that. The inner product here is going to be 2n. The outer product here is going to be 10n. And there's no way you can change these signs to combine to negative n. If they're both positive, it's 12n. If they're both negative, it's negative 12n. And if you have opposite signs, you either have positive or negative 8n. So that unfortunately doesn't work. Okay, so let me scratch that off. Now what we can try instead is the same numbers 5 and 2, but in the opposite order. And if that doesn't work, then we'll have to try 1 and 10. Or 10 and 1, so in some order. But 5 and 2 actually works. Notice if you check the inner and outer product, you get 5n and 4n. And the way that these can combine to a negative 1n, which is negative n, of course, is that the top is negative and the bottom is positive. So branching back, this would be positive and that would be negative. Perfect. So you can check the foiling process, but this essentially checks it as we go along. So that'll definitely work out. It's fun to do it so you see all the moving parts kind of collide together. And then by using our methods of setting these equal to 0 and so on, by changing signs and dividing by numbers in front. Change the sign of this, get positive 5 divided by the number in front. So n is positive 5 over 2. Change the sign of that to negative 2, and there we go. Okay. Now this one, in order for us to undo this, we can't just square both sides right away. We have to get the radical by itself first. If you think we can just square each term, you're wrong. Sorry to say, but that's not how things work. You have to square each side, and when you square this side, it's a binomial squared. You have to FOIL it out, and you still get a radical left, unfortunately. So the only way around this is to move this 5 to the other side by subtracting. Then we have the radical isolated. Then we can square both sides. But just looking at this, I can tell there's no solution. Oh, by the way, I didn't check these ones. But some kind of little bit of advice I want to give you is that if you have a cubic scenario, so a cube root, or any odd root for that matter, there'll never be an extraneous solution. And that's because an odd root can have a negative on the inside. And a negative to an odd power is a negative. So you could have a negative as a result. And those are the scenarios where you get possible extraneous solutions with radical equations. But really, it's only when you have an even root. So for the odd root ones, there's no extraneous solution. So I knew that with confidence. But if you want to check these, you can plug them in, and you'll see that you'll get the cube root of 8 for both of those, actually. So plug in 5 over 2 or negative 2, the inside will be 8 for both of those. But for this one, the square root, that's a positive value, but this 7, that's a negative value. So there's no solution right away. Now, if you want to see that by actually going through the process, we'll square both sides. That squared cancels the radical. And you see that we have x minus 5 is equal to 49. So you add 5 to the other side, you get 54. X equals 54. But it's not a valid solution. And the reason why is because when you plug it back into the original, you get, well, let's see, 54 minus 5, that's 49. The square root of that's 7, but 7 plus 5 is 12, not negative 2. So as it turns out, believe it or not, by checking, this is indeed an extraneous solution, meaning that there's actually no solutions, unfortunately. So I think that's kind of sad news, but I guess the good news there is that we could have seen it ahead of time that, oh, we have a radical equals a negative. That can never happen, unless there was a negative in front of the radical. Kind of strange, but squaring both sides gets rid of negatives, so you have possible scenarios for extraneous solutions. Great, so that was 9. Now let's move on to number 10. Okay, so I actually referred to these problems earlier, and I mentioned there would be a problem in the review somewhere where we have to solve by quadratic formula or some other means besides factoring, because factoring wouldn't work. So factoring can sometimes not work, and you have a quadratic equation that has solutions, but they're not rational, meaning that they're not fractions of integers, so they wouldn't come from factoring, as it turns out. So if you move everything to one side, so the zeros on the other, kind of like we have here, but not quite here. In fact, we need to do that anyway, so I'm just going to subtract that 3 to this side ahead of time. That's okay. We'll talk more about that in a moment, once we get here. But if you look at these, they're actually not factorable. You may think this one is, because there are two numbers that multiply to 3 and then add to 4, but with the signs it doesn't work out. So instead we're going to use different methods. Now you can possibly get complex solutions from these where you get negatives inside of radicals and so on. I don't think that happens in these, but we'll have to see. Now, completing the square, or CTS for short, has to do with the fact that x plus a number squared is x squared plus 2 times that number times x plus that number squared. There's actually a backwards way of thinking of it, is that if you replace b with b over 2, 2b over 2 is just b. This is b over 2 all squared, and that's b over 2. And really, the recognition is that since you have 2 times the product for the middle term, then if you take half of the middle term, then 2 times x times this half of that will just give you back b times x. It's kind of strange, but it basically says that if you were to add half of the middle number squared, it makes that trinomial, well, it turns it into a trinomial that is a perfect square. So I'll show that here, but this 3 we need to get rid of. So I'm going to add the 3 to the other side. So I'm going to isolate the x squared and x term, add some magic term to each side, that's positive 3 now. And the magic term we add, according to this, is half of the middle term squared. Half of the middle term is 2, 2 squared is 4. So on this side we get 7. On this side we get half of this plus x, so x plus half of that's 2 squared. So notice when you actually FOIL this out, it checks out x squared plus 4x plus 4. So there we go. So to undo the square, we're going to square root both sides. Now when you do that, you get a plus or minus on one side. The square root of this, it cancels the radical. Square root of this, we get a plus or minus on this side. Okay. Why the plus or minus? Well, as we saw earlier, when you square a positive or negative, you get positive no matter what. So square rooting, you technically get 2 scenarios, either a positive scenario or a negative scenario. Finally, we have x plus 2 is equal to plus or minus radical 7. Subtract the 2 to the opposite side, we get our answer x is equal to negative 2 plus 7 or negative 2 minus 7. I meant to say radical 7. There we go. I'm writing it, of course, here with the plus minus notation. Okay, so now what about quadratic formula, QF for short? So quadratic formula, so this is what I had to say for completing the square. So what I have to say for quadratic formula is that if you have the equation ax squared plus bx plus c, so a general quadratic, you can actually solve for x using this formula, negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. Now, if you wanted to, you could have actually used this method here as it was at the very beginning. Now, since I'm asking you to do this method, you have to do it this way, but if you don't like it or you're not sure and you're confident with quadratic formula, you can use that in part A to check your work to make sure you're on the right track to get this answer indeed. So you can definitely do those things. But here, now that we have everything on one side to the zeros on the other, we can label each of those coefficients as A, B, and C. Keep in mind the negatives. So here, A is 3, B is negative 2, and C is negative 3. Perfect. So now, using quadratic formula, what we end up getting is the following. X is equal to negative B, negative 2, plus or minus the square root of B squared, it's negative 2 squared, minus 4 times A times C, so it's 3 times negative 3. You divide everything by 2 times A, which is 2 times 3. Okay, so now what do we get? We get a double negative that's positive 2, plus or minus the square root of, I usually like to do this off to the side, but negative 2 squared is positive 4. Okay, that double negative is positive. 4 times 3 is 4 times 9, which is 36, so that's 40. So we get square root of 40, actually. So let me just cut that off. And then over 2 times 3 is 6. So there we go. Now, this actually simplifies a little bit more, so you have to be kind of careful here. Now, granted, that's kind of minor, but it's still part of the solution. I want you to simplify it as much as you can. So it's called simplified radical form. So The way you do it is you look at the radical and you see if you can factor out anything that can be square rooted. So, in fact, it's 4 times 10. 40 is 4 times 10. So let me write this. The square root of 40 is the square root of 4 times the square root of 10. But since the square root of 4 is 2, this is 2 radical 10. So it may not seem like much, but we have 2 plus or minus 2 radical 10 now, all over 6. So if you pull the 2 out from the top by dividing these by 2, then you can cancel this 2 with this 6 to get 3. So what we have left is 1 plus or minus radical 10 all over 3. So it's x equals that, but let me write it, I guess, over here. X equals 1 plus or minus radical 10 all over 3. And there we go. Fantastic. Now moving on to number 11, finally. Okay, so for this problem 11, I asked you to solve these, and I specifically emphasized to solve by any method. And the reason why I say that, I think, is because each of these corresponds to a quadratic equation that you can solve by factoring or quadratic formula or completing the square if you want. So you can use whichever one you want, opposed to 10 where I emphasize what you should use. So it's not obviously correspond to a quadratic, but we'll see that as we go along. Now, for an equation involving fractions, what you generally want to do is clear denominators and multiply them by the LCD. Now, in this case, the LCD is just the product of these denominators. They have nothing in common. So the LCD is going to be their product, 3 times x minus 1. So I'm just multiplying them by writing the 3 in the front. Okay. So generally what I advise is you treat this LCD as, well, you're going to multiply everything by this, but it's kind of like a filter that filters out denominators. So if you multiply each of these terms by the LCD, what you end up getting as a result is a new expression for each one, new term kind of for each one, but there's no denominator now. So the denominator has been so-called filtered out. So notice with 1 over x, the x's cancel, so the top 1 is just multiplied by what didn't cancel, which is that 3 and that x minus 1. Okay. Similarly here, the x minus 1 cancels, so the top 2, it's plus 2, is multiplied by what didn't cancel in the LCD, which is 3x. And then here finally we have 4, the top, times, well, the 3's cross-cancel, so we just have x times x minus 1. So this is a quadratic. I'm going to simplify and write that above here, and then I think we may be able to solve this by factoring. Let's see. So distributing that, that's 1 times 3 is 3, so we can ignore that one part. So that's 3x minus 3. 2 times 3x is 6x. Equals, distribute this 4x. You have 4x squared minus 4x. Okay, let's move everything on one side so the zeros on the other. I'm going to actually push those to the left side. And these, notice, combine to 9x. So I'm going to subtract 9x like this. So that'll cancel these two. And we'll, of course, add 3 as well. Cancel that one. So I'll write that plus 3 here. So let's see if we can see that. We get 0 on one side, and then on the other side we get 4x squared minus 13x. There we go. Plus 3. Now you can try whatever method you want. I'm going to do this by factoring, and it is factorable actually. And I can tell because of that AC method. 4 times 3, those outer two terms, that's positive 12. The two numbers are multiplied to that, but add to negative 13, the middle coefficient, are 12 and 1, both negative. That ends up working. So since we have a 4x in front, we'll draw a line through this and write 4x without the square. This one doesn't reduce, so I know one of the factors is going to be 4x minus 1. And the other factor we can just see by either reducing this or just kind of completing what we need, kind of filling in the gaps, filling in the blanks. So 4x times x is 4x squared. But negative 1 to complete the last guy here needs to be multiplied by negative 3. And you can clearly see that 4 over negative 12 reduces to 1 over negative 3 indeed. So now this being equal to 0 means that x is either equal to positive 1 over 4 or positive 3. Now, you must check for extraneous solutions, but instead of plugging them in, I'll tell you right now that for equations that involve denominators, basically, You just want to make sure you don't get a zero denominator. Well, we could have checked ahead of time that the zero denominator only occurs when x is either equal to 0 or 1. So we cannot have those. If x is 0, zero denominator there. If x is 1, zero denominator there. But notice we didn't get either of those, so these aren't extraneous solutions. So these are indeed our solutions. And again, you can check that if you want, but that definitely works. Okay, now for this one, if you wanted to, you could actually solve this the same way we solved the radical problems before. But I'm going to notice something a little clever. This reminds me of x squared minus 5x plus 4. So I'm going to use the substitution t is equal to radical x. That means we're squaring both sides, t squared is just x. So then now using this becomes t squared minus 5t plus 4 is equal to 0. So factoring the two numbers and multiply to 4, positive 4, and add to negative 5 are, well, let's see, does it even work out actually? Yeah, I'm sorry, it works out. It's negative 4 and negative 1. So again, similar to this, double negative. So right, so that works. They multiply to positive 4, add to negative 5, good. So we get t minus 4 times t minus 1. So that means t is either positive 4 or positive 1. Great. But now, if you look at what t was really the square root of x. So that means the square root of x is either 4 or 1. So you basically have to look at each of those equations and square both sides to undo the square root. So I'm just going to write it like this, which kind of sounds weird, but I'm squaring each term, okay? So if you square the the radical x, that cancels the radical, and you just get x. Square 4, you get 16. So that's for one of those scenarios. We understand that we're kind of handling two different alternate scenarios at the same time. And then when radical x is equal to 1, squaring both sides, you get x is equal to 1. Now we kind of have to check these, of course. Notice 16 minus 5 times the square root of 16, that's just 5 times 4, that's 20. 16 minus 20, that's negative 4, plus 4, that's 0. So 16 works. What about 1? Well, 1 also works, actually. You get 1 minus 5 times radical 1, that's just 5. So 1 minus 5 is negative 4, plus 4 is also 0. So these actually both work. No extraneous solutions there. How interesting. Great. So that was 11. Now moving on to number 12. Okay, so for number 12 here, we're asked to solve these inequalities. I don't know if I emphasized to write our answer in interval notation or not. I'm looking at it right now, and I don't. But I'm going to write my answer in interval notation. I think that's probably better. And in fact, it's better because it goes along with the process I like to show, and that is to solve the related equation and then pick values around those solutions, and then check to see which intervals you take the union of, depending on what checks out in the inequality. So let's see. So to solve the related equation, I'm going to move everything on one side so the zero's on the other. So subtract that 2x from the right to the left. Now, if we just imagine that that's equality, you can solve that, but how you would solve it would be by factoring. So what I'm going to do instead is I'm going to factor this, but leave that inequality part. So this factors as x minus 3, x plus 2. Sorry, plus 1 I meant to say. Right, those multiply to negative 3 and add to negative 2. So I'm not writing the x here, but we can see that hopefully. So now, if this was equality, then x would be equal to 3 and negative 1. So these aren't solutions quite, but these are going to surround our intervals that will possibly act as solutions. So I'm going to create a number line here and plot these values we found from the related equation, meaning that if this was equality, those would be the solutions to that equation. So that's known as the related equation. So in order, we get negative 1 first, then 3. Okay, going from left to right. And of course, negative infinity is way up here, and positive infinity is in that positive direction. So that we know. In fact, if you want to write these as intervals, this is the interval negative infinity to negative 1. This is the interval 1 to 3. This is the interval 3 to infinity. So these are the intervals that we're going to be taking the union of, possibly, depending on which ones work and which ones don't work. How do we know which ones will work or not? We're going to test them by plugging in test points. So the test points are going to be values that are around these solutions from the related equation. So we're going to test the following. Let me kind of border this off a bit. So here in this region, I'm going to test any number negative, less than negative 1 works, so let's say negative 2. Here 0 works, and here 4 works. So the general rule of thumb is to pick something not too far away from your test, not your test point, but nothing too far away from your solutions that you got here. But also, if you're in between a positive and negative, pick 0. So if you can't pick 0, pick 0. So I'm going to plug these into the original. And in order to plug them into the original, we'll have to see if it works or not. So if you plug in negative 2, you get negative 2 squared, that's 4. 4 minus 3 is 1. But 2 times negative 2 is negative 4. 1 is now less than negative 4. So that doesn't work. Now, as it turns out, there's a better way of checking. The better way of checking is this factored version here. That's why I left it like this. So if you plug in negative 2, you see the negative 2 minus 3 is negative. And negative 2 plus 1 is negative 1. So it doesn't matter what the numbers are. The whole point is the sign. It's negative times negative, that's positive. But hang on, this says it's less than 0, which means it's negative. So that doesn't work. So this doesn't work. So this doesn't work. Plug in 0, you get negative times positive. That is negative, so that works. So we're going to keep this guy. Plug in 4. 4 minus 3 is positive. 4 plus 1 is positive. Positive times positive is not negative, not less than 0. So that doesn't work, so we only keep the middle one. So the answer is indeed 1 to 3, and it's open. So we don't change those parentheses to brackets, we leave them like that. How do I know that? Well, because the inequality was not or equal to, unlike this one's or equal to. So we'll see how that plays out with B, but that was it for A. Fantastic. So now let's move on to B here. Now B is the same exact idea, only the solving part is kind of strange because since we have denominators, we also have to consider when those are 0, as it turns out. So if you solve this, you get x plus 2 is either 0, which means that x is equal to negative 2. Now, what I'm doing there is I'm pretending this is equality, and I'm noticing that a fraction is equal to 0 when the top is 0. So that's how I got this. Okay? But then also we have to consider when the denominator is equal to 0. So denominator being equal to 0 gives me x minus 1 is 0, which tells me x is equal to positive 1. So these are the numbers we're going to be using to surround our soon-to-be test points, much like we did with the above problem. So in order, we have negative 2, then 1. So negative infinity here, positive infinity here. Let's write these intervals. Negative infinity to negative 2, negative 2 to 1, and 1 to infinity. Now, because this symbol is or equal to, we'll have to change some of these parentheses, some, not all of them, to brackets eventually, but I'll do that at the very end. Now, what are we going to test, though, I think is the big question at hand here. So here we'll plug in negative 3. Here we're between a negative and a positive. We can pick 0. And here we can pick 2. Okay, so I'm going to plug it in. Now, this is kind of already factored. Just have a numerator and denominator. So we can do the whole sign scenario we did here. Right? Positive over negative would be negative. Positive over positive is positive. Negative over negative is positive, and so on. So when you plug in negative 3, you get negative on top, negative on the bottom. It's negative 1, negative 4. But it's negative over negative, that's positive, and bigger than 0 means positive. So this guy works. So we're going to select this. It doesn't mean that that's our answer. It means we're going to union it to everything else that's selected, if possible. So I don't know if these will work out or not, but let's see. When you plug in 0, you get 0 plus 2 is positive, 0 minus 1 is negative, so positive over negative is negative, not positive. So that doesn't work, so we reject this one. Plug in 2. Well, let's see, we get 2 plus 2 is positive, 2 minus 1 is positive, positive over positive is positive, greater than 0 is positive. So this checks out, so we also select this one, so we take the union of those results. And now here comes the fun part. Since we had an or equal to, then we can change some of these parentheses to brackets, possibly. Now, which ones you change are the non-infinite ones and the ones that did not come from the zero denominator. I'll explain that in a moment. So the non-infinite ones are left as parentheses, and the one that came from the denominator being 0 will also stay as a parenthesis. And again, since it's or equal to, we have -2 as a possibility. So why did the 1 stay? The parentheses on the infinities, I think, is pretty self-explanatory. You can't be equal to infinity or negative infinity. They're just figurative. But the reason why 1 has to be excluded, why it's parenthesis and not bracket, is because if x was 1, you get a 0 denominator. So you can't plug it in anyways. Not that it doesn't work out in the equality sense, but it doesn't work out in a mathematical sense. You get an undefined value. But -2 works, you get 0 indeed, and since this is or equal to, that definitely works. So this is our answer then. Great. So now moving on to number 13. Right, so for 13 here, we're asked to find these 4 things given this function f of x and this function g of x. So these are known as combining functions. So you can combine functions using operations. For example, you can add functions, subtract functions, multiply, divide, and even take a function of another function. That's known as composition. That's what these last two are. So this open circle is not it's not multiplication, it is composition. So it's best often thought that this O stands for of. Okay, so you can take f of g of 1, and here you take g of f of x. So we'll get to those after, but let's focus one at a time first. So the way it works is when you have a combination of functions with an operation, you just apply the operations to those functions in that order. So here, g minus f of x is the same as g of x minus f of x. So it looks like distribution of this x, but it's really thought of that this function is a new function that is made up from g of x minus f of x. It tells you what to do with those functions of x. So g of x is this 2x plus 1. Minus f of x is that. We need parentheses there because we're subtracting the entire quantity. Distribute the negative. We get 2x plus 1 minus 2 plus x squared. These combine to -1. So we're left with x squared plus 2x plus 1. Minus 1. And that's the final answer for this one. Great. Okay, so now for this one, we have division of these functions but evaluated at -1. And if you wanted to, you can find the division of those functions evaluated at x. You get a new function, and then plug -1 into that function. That definitely works. But here I'm going to apply this a little more directly and take f of -1 over g of -1. So f of g of x, f over g of x is f of x over g of x. So here x is -1, so you can just take f of -1 literally over g of -1. So I'm going to evaluate f at -1, g at -1. F at -1 is 2 minus -1 squared. -1 squared is positive 1. 2 minus 1 is positive 1. Over g at -1, that's going to be 2 times -1 is -2, plus 1 is -1. So all in all, we get -1. Fantastic. So now this is g, or I guess f of g of 1. So the way we write that is f of g of 1. So I'm going to work from the inside out. So g of 1 first. So g evaluated at 1 is 2 times 1 plus 1, so it's 3. So now we have to evaluate f at 3. So that's how that works. So when x is 3, we get 2 minus 3 squared. Let me just write it out. 2 minus 3 squared. That's 2 minus 9. That's -7. Okay, so I hope we can follow that. There's kind of a nice diagram that I want to show, and that's that we jump from g to f to get to the final f of g. So you plug 1 into g to get 3, you plug 3 into f to get -7. So in reality, this is plugging 1 into f composed with g like that. It's kind of this 2-pass diagram. So now here it's something similar, but this is g of f and it's of x, not of a number. So this is g of f of x. So let's see, how does this work? Well, f of x, the inside, is 2 minus x squared. So it's g of 2 minus x squared. What does that mean? Well, it means everywhere we see an x in the g equation, we're going to replace it with the entire inside here, which is 2 minus x squared. So g is 2 times x plus 1, but x is the inside 2 minus x squared. Okay. Now we distribute this 2, we get 4 minus 2x squared plus 1. The 1 and 4 combine to 5, so our final answer here is 5 minus 2x squared. Perfect. So now we can move on to problem 14. Okay, so for 14 here, these are both, well, they're exponential equations, and you can solve them a few different ways. Well, the way I want to show is by what is called finding common base and using this one-to-one property, or sometimes referred to as uniqueness property of exponents. So I'm going to notice that the common base here between 4 and 32 is 2, meaning that 4 is 2 to something and 32 is also 2 to something. It may not be super obvious at first, but once you look at powers of 2, you'll see that 2 squared is 4, and 32 is 2 to the 5th power. And that should have been an x, sorry, not a 4. So 2 squared, that's 4, so 4 to the x is equal to 32, but 32 is 2 to the 5th. So using an exponent property, we can multiply those to get 2 to the 2x is equal to 2 to the 5th. And now using this one-to-one property, or uniqueness property, basically says that if you have the same base, then the powers must be the same. So that means 2x must be equal to 5, divided by 2, we get x is equal to 5 over 2, and that's it. Now, of course, not the only way of solving an equation like this. Another method that works is you can get logarithms into the mix. And in fact, if you convert this into logarithmic form, you can see that right away this is log base 4 of 32 would be x. So you can compute this with your calculator by using change of base formula, recognizing this is just log of the inside over log of the base. And your calculator will just give you 2.5, which is 5 over 2. So that works too, but it's a little, I don't know, less direct, I guess. Here, I'm not going to use the logarithmic explanation. I'm just going to go straight for it using this idea, common base. 3 is just 3 to the 1. You can't write that as any lower power. 81 is 9 to the second, but I want the same base. And notice 9 is 3 to the second, so that's 3 to the second, which is 3 to the 4th. So this is 3x plus 2 equals 3 to the 4th. Using uniqueness, drop the base, we get x plus 2 is equal to 4. Subtract 2, x is 2. Now I didn't check these, but of course you can check these as well. Okay, so moving on to number 15 now. All right, so these problems are a little bit different. The first one's a logarithmic equation, and the second one here is an exponential equation, much like we saw with 14, but this one's actually way harder to do. You can't actually write 2 and 3 in terms of the same base. Well, you can, but it's not going to be pretty. But we'll get to that. First, we want to combine these into one logarithm using the product rule. That's because there's a plus here. If it was a minus, you can divide the insides, but a plus, you multiply the insides. This is log base 2 of the product of these. So it's x times x plus 1. Product of the insides, that is. You can distribute this to get x squared plus x. That's log base 2 of x squared plus x equals that 1 still. And now converting this to exponential form, we see that the base 2 to the power 1 is equal to the inside. 2 to the 1 is equal to x squared plus x. We can move everything over to one side so the 0 is on the other by subtracting that 2 to the right side, and we rearrange that a little bit. That factors as x plus 2 times x minus 1. Setting these each equal to 0, we get x is either equal to negative 2 or positive 1. Before I box this, we must check for extraneous solutions, and that's when you have possibly 0 or a negative inside of the logarithm. That would imply that 2 to a power is negative or 0, but 2 to any power is only positive. So notice when x is negative 2, you get a negative 2 right away on the inside. So it's a negative value, so that's contradiction. The negative 2 plus 1 also is negative, but one of them suffices. So if one's negative, then that whole solution is poisoned. So this is extraneous. 1 works. When you plug in 1, that's log base 2 of 1, which is 0, by the way. And this is log base 2 of 1 plus 1, which is 2, but log base 2 of 2 is 1. So we can actually simultaneously check that we get 0 plus 1, which is 1. So not only did we check it's not an extraneous solution, but we also verified it is indeed a solution. So our final solution here is x is equal to 1. Great. So definitely a lot going on there in that one. Now, for this one, there are a few ways of doing this, but the best way, I think, what we've seen actually in the previous review, I believe, is to move everything over to try to write a single power of x on one side. So in fact, we can do that by splitting this up kind of as 2 to the x times 2 to the negative 1, which really means over 2. And then I'm going to move this x factor over, and you can actually move them over however you want. So if you want to divide this 3x to this side, and then multiply that 2 to that side, you can do that. I say multiply because it's really 1 over 2, so you can multiply the 2 to cancel that. But I'm actually going to divide both sides by this 2x. It may not seem obvious right now why, and it kind of seems a little weird, but just kind of bear with me. 2 to the negative 1 is 1 over 2. There we go. And this really is 3 over 2 to the x. Perfect. So that's what we want. We want to write it as something to the x equals something. Then we can use logarithms. So writing this in logarithmic form actually does it and completes the problem, basically. There's a little more we can say beyond that, but this is basically it. Okay, so converting this to logarithmic form, the power x is equal to log base, the base, which is 3 over 2, of the inside, which is 1 over 2. Perfect. So that's it. This is the answer. This works out. Now, there are different representations of this if you want. Since the inside is a fraction, you can write this as log base 3 over 2 of 1 minus log base 3 over 2 of 2. But log base anything of 1 is 0, so that's just actually negative that. So in fact, we can write this as negative log base 3 over 2 of 2. That also works as a solution, just as acceptable. What else can you do? Well, you can actually write this as ln of the inside over ln of the base using change of base formula, kind of like we saw with 14 when I explained 14a earlier, but I used a log instead of ln there. But here I'll use ln. It's kind of interesting, but you get negative ln of the inside over ln of 3 over 2. But ln of 3 over 2, using a similar idea we said earlier to get from here to here, since it's a division on the inside, you can write this as ln of the top minus ln of the bottom. So that's a quotient rule, kind of like how we use product rule here, but here it's quotient rule. So multiplying the insides means you're adding the logs of those, but dividing the insides means you're subtracting logs of those. So in this case, it's I'm using ln. It's going to be ln of 3 minus ln of 2. What's kind of curious is that we can actually absorb this negative into the denominator by switching the order there. So even though this is acceptable, it's also acceptable even beyond this, is x is equal to ln of 2 over ln of 2 minus ln of 3. Now that was just me basically absorbing the negative into the denominator, distributing that, and then getting a positive ln of 2 and negative ln of 3. Now I know I kind of went a little bit of a tangent there. Of course, any of these will do. I think this probably looks the nicest, but I don't know. Even approximating, I guess, would be okay, but I kind of would like to see an exact form if you could. Now, there are different ways of doing this. You can take ln of both sides from the get-go, bring the powers out, and then maybe approximate ln of 2 and ln of 3 to your desired decimal place. Maybe 3 or 4 places would work. And then solve that linear equation from there, but then you're kind of approximating as you go along, so it's less exact. This, I think, is more accurate, but maybe that's just me. So that's 15. Now we're going to move on to 16. Okay, so for 16 here, we're asked to find an equation for each of these scenarios. For part A, we have a circle with a center of 2, 0 and a radius of 4. Now this is a pretty generic thing. When you have a circle of center hk and radius r, then the equation of a circle is then x minus h squared plus y minus k squared equals r squared. Essentially, it comes from the distance formula, just kind of squaring both sides to cancel the radical into distance. formula. Now, the reason why the distance formula comes up is because every point on the circle has the same distance away from the center, which is the radius. So you end up getting this formula out, actually, where hk is the center of the circle. Now, if h is 2 and k is 0, you get x minus 2 squared plus y minus 0 squared equals r, which is 4 squared. And this just simplifies to x minus 2 quantity squared. Y minus 0 is just y, so I'll just leave that as y squared. And then 4 squared is 16. You don't actually have to expand that x minus 2 squared out. You can, I guess. But then it gets weird because you get a plus 4 as the last term, and you could like move that over and combine it with 16. And then it kind of gets a little iffy on what a standard form is. This would be standard form. So I'm going to leave that as the answer. Okay. Parabola opening to the right with a vertex -2, 5. This is a little strange, but remember from what we've seen before with parabolas, is if you have an upward or downward parabola, it has a vertex h, k, and the equation for the parabola then would be y is equal to a times x minus h squared plus k. Now, if a is positive, it opens up, and if a is negative, it opens down. Now, a tells you basically how skinny or wide the parabola is, but we don't actually have any mention of that. So I'll probably specify more in the exam, I think, maybe, hopefully. Otherwise, you can just let a be whatever you want. So I'll just assume a is 1 or -1, depending if it's opening in the negative direction. But we have more of an important issue, and that is that this opens to the right, not up or down. So this is not a vertical parabola, but this is a horizontal parabola. Now, for horizontal parabolas, it's the same thing, only you switch the y's and k's with the x and h's. So that's for vertical. For horizontal scenarios, the formula is a little different. It's x equals a times y minus k quantity squared, but plus h. So x and h swap with y and k. And now, this will open in the positive direction if a is positive, and then the negative direction if a is negative. So to the left if a is negative. But now notice that this hk vertex will still maintain hk. Why is that? Because since y is next to k and h is still corresponding to x, then we still have the fact that h is an x value and y is a k value. Sounds strange, but it is definitely true. So if this is h and this is k for the vertex of this parabola, then we have the following. And again, we're assuming here that a is equal to 1. I know it's positive because it's opening to the right. If it was negative, if it was open to the left, it would be negative. So we can make it -1, for example. But here we go. So we get x, there we go. X is equal to a, which is 1, times y minus k, y minus 5 squared, plus h, which is -2. So I'll just write -2. And there it is. I'll actually expand this a little more. So if you expand out, the 1 doesn't do anything in multiplication. But if you expand this out, you get y squared minus 10y plus 25, but 25 minus 2, of course, is 23. So there's our answer expanded out. Awesome. Great. Now, finally, we'll move on to 17 to conclude the review. Okay, so finally for 17, we're asked to find if each of these equations represents a hyperbola or an ellipse. So we state that. And then we find the vertices and center for each of them. So what's that about? Well, long story short, ellipses and hyperbolas basically kind of behave the same, but one's inside out of the other. Now, the way you can tell which one's which is that hyperbolas have a minus in between and ellipses have a plus in between. Now, the standard form for each of them look pretty much the same. You have x minus something squared, y minus something squared, and then over, or I guess under each of them, you have denominators. And the square roots of those denominators are what we call a and b, which are basically the kind of horizontal or vertical distance you move from the center to get to these kind of endpoints of something. So I'll explain that actually with this one. So here for ellipses, I know it's an ellipse because it's a plus in the middle. And I should mention, with the standard form of an ellipse and for hyperbola, you want one to be on the opposite side. So here we have a little bit of work to do, but we'll get to that one later. So the square root of the number under the x factor is 7, and the square root of the number under the y factor is, it's 5. I'm kind of jumping the gun a bit, but for ellipses, the larger one is what we call a. For hyperbolas, the one in front of subtraction for the denominator is what we call a. So they behave a little differently. Okay? So I knew that 7 was a because the larger one is 49. So if you square root these, you get 7 and 5, but the larger one is a, and the smaller one is b. Okay. So that doesn't necessarily matter too much, but I think what does matter is the kind of distance you travel from the center. So let's plot the center. So what is the center? It's what's subtracted from x and what's subtracted from y. So I'll write capital C for center. What's subtracted from x is 1, what's subtracted from y is -2. Kind of think from what we saw with a circle, it was x minus the x value of the center, y minus the y value of the center. So very similar ideas. Y minus -2, notice, would be y plus 2. So there we go. Essentially, it's a sign change of the numbers next to x and y. Sign change of -1 to get +1, sign change +2 to get -2. But now, what about the vertices? Well, here I'm going to show you with the graph to see what's going on. So we're going to go to 1, -2, which is down here, let's say. And we're going to go up and down by the square root of the number under y, which is 5. So we go up 5 from this point, we get 3 above the x-axis. It's right here. And if you go down 5, 1, 2, 3, 4, 5, assume that's good, you get to that point. So my scaling should be, I'm trying to make it exact, but it may not be super accurate. But these are supposed to be the same distance, 5. So now we're going to go left and right by the number under x. X for horizontal, y for vertical. So that should make sense. I'm going to go to the right 7. 1, 2, 3, 4, 5, 6. More. Do that. There we go, 7. So we get there. And then we go to the left 7. So it's 1, 2. Oops. There we go. 3, 4, 5, 6, 7. So we end about there. So we end up getting these endpoints of the ellipse. So an ellipse, probably should have mentioned earlier, is an elongated circle. So this is stretched horizontally. And the way you can tell just by looking at the equation is the larger denominator tells you if it's horizontal or vertical. The larger denominator is under x, so that can tell me right away that it's horizontal. If the larger denominator was under y, then it would be vertical. So that's kind of sloppy, but it looks more or less like an elongated circle. But there we go. Now the vertices, you can think are just the endpoints, right? But not really. So the vertices for an ellipse are defined to be the ones on what is called the major axis. So the ones that are further away. So this would be the major axis, and this would be the minor axis. So these 2 points are the vertices. You can call them V1 and V2. I'll call them V1 and V2. So in this case, notice we can just count. We know the y value is going to be -2, same as what the center was. So there's no vertical change there. There's only horizontal change. So something to think about. Now, if you add 7 to this x value 1, that was 2, 3, 4, 5, 6, 7, 8. You get to 8. That makes sense. 1 plus 7 is 8. Now, similarly, 1 minus 7 will be -6. So you can count. That's going to be 0, -1, -2, -3, -4, -5, -6 indeed. So our vertices are V1, what I'm calling V1, is -6, -2. What I'm calling V2 is 8, -2. And yes, there is kind of a shortcut. What's the shortcut? Find A, and you do plus or minus that A value to either the x or y value of the center, depending which one the larger one is. The larger one is under x, so we apply that plus or minus 7 to the x value. Plus 7, you get 8. Minus 7, you get -6. That's the shortcut, but the visualization really ties it together. Okay. So now for hyperbolas. So first off, the standard form is to get 1 on one side. There's a 36, so we're going to divide everything by 36 naturally. A cancellation, that's 1, just like we want. 4 goes into 36 9 times. 9 goes into 36 4 times. So we get x squared over 4 minus y squared over 9. Now, if you look at the whole x minus a number, y minus a number, we don't have that here. You can think of this as x minus 0, y minus 0. We kind of saw that with the circle problem. Y minus 0 was just y, so we had y squared. So if you have no number next to x and y, then the value for the center of that x and y value would be 0. So in this case, for both of them, it's 0. So the center is 0. And I probably should have mentioned earlier, I think I did say that earlier, this is a hyperbola, and we can tell because of the minus in between. Okay? So I'll box that. Now the center, just like we just discussed, is 0, 0. Perfect. What about the vertices? Well, much like with the hyperbola, you go up and down by the square root of the number under y, and left and right by the square root of the number under x. Only, here a is not the larger one, here a is the one in front of subtraction, which is this one. So a is going to be the square root of 4, and b is going to be the square root of 9. Okay? So here's what you do. You start at your center. You go left and right, it's horizontal, it's x, by the square root of the number under x, which is 2. So you go left and right by 2. You go up and down by the square root of the number under y, which is 3. So go up and down by 3. From here, you can create what I call the dotted box. That works. Then you can create these diagonals, which pass through the center and the corners of this box. Okay. And now the important piece is we have these kind of these endpoints, which kind of remind me of the endpoints we had here for the ellipse. Only we're not creating an ellipse; we're writing this dotted box first with these weird diagonals, which kind of looks like an X. Now, these are called asymptotes. They're not actually super important, but it kind of gives you an idea of what the shape looks like pretty accurately. So it's nice to mention it. Now, here, the larger denominator told you if it was horizontal or vertical. But the way the ellipse is structured, you kind of see that anyways. But here, not so much. Here, you have to know which one's in front. X is in front. So that means I'm going to use the horizontal points, not the vertical ones. And what I do now is I create opposite-facing parabolas that hug these asymptotes. So one will look like this, and the other will look like this. So the only point of that x is just tell me how wide these parabolas are. If the x's were slanted more, then we'd have skinnier parabolas opposed to these wider ones. Okay. Now, what's the point? Well, we don't actually really need the image for answering this problem. Much like we didn't really need the image here, there's kind of another way of doing it. But more importantly, the vertices are what we're after, right? Found the center, but now the vertices. And the vertices are just the vertex for each of these parabolas. So you have one here, which is 2, 0, and one here, which is negative 2, 0. So I'll just write v equals plus or minus 2 comma 0. If you want to write v1 is negative 2, 0, and v2 is 2, 0, that works. And again, it doesn't matter which one you label as v1, v2, but I think this is fine with plus or minus notation. Okay, great. So that concludes the video for the final exam review. Really hope you all enjoyed this, and I really hope you all enjoyed the class as well. It's been great having you all, and I hope you've been enjoying the videos I've been doing here. So with that being said, I wish you luck in the exam, and that's it. Good luck.